Hello everyone, my name is Aisha Siddiqa and I'm excited to present the project I worked on during my internship at Emertxe Information Technologies. The title of my project is Washing Machine Prototype. This internship has been an incredible opportunity for me to apply classroom knowledge to real world problems. I was able to design, code, simulate, and test an embedded system that mimics the behavior of a modern washing machine, also using tools and technologies commonly used in the embedded systems industry. So, what is this presentation about? Over the next few slides, I will walk you through what I learned during this internship, the core objectives of my project, the tools and components I used to bring it to life, a detailed demo walkthrough, and finally, I'll share a summary of what I gained from this journey. This experience taught me not only how to work with microcontrollers and simulation tools, but also how to approach system design, break down problems, and build confidence in debugging and testing. This was not just an academic project, but a real step into the industry style workflow. From requirement gathering and design to implementation and testing. Let's dive into what I learned during this internship. This internship gave me theoretical depth and hands on skills in embedded systems development. Let's begin with the programming foundation. We started with embedded C programming, unlike general C programming. Embedded C demands writing code that runs directly on the hardware. I learned how to use loops and conditionals to control hardware behavior, use memory efficiently, work with register and ports directly, write modular code for better debugging and maintainability. Next, what worked on the Pixim Pic, PICSimLab in PIC16F877A Microcontroller, which is an 8-bit microcontroller with a rich set of features. Here's what I explored: its architecture, how the ALU memory and registers are structured, internal modules like timers, ADC, EEPROM, flash, and GPIO ports. I learned how to configure the ports, use the timers, and set up interrupt routines. One of the most interesting part was working with hardware components. Let me highlight a few key ones. LEDs used to indicate various washing cycles like wash, rinse, and spin. Buzzers used to signal the end of the wash cycle or provide alerts. Fan. In place of a real motor, a fan was used to simulate the spinning action of a washing machine drum. CLCD. Character LCD 16 into 4. This was used to display messages like washing, paused, completed. I learned to interface this LCD in 4-bit mode. Keypad. The 4 into 3 matrix keypad was the input device. It allowed users to select washing modes, water levels, and perform actions like start, pause, resume, or stop. Each component taught me something important: timing and real time control using delays and interrupts, debouncing keypad inputs, synchronizing outputs actions like starting the fan when washing begins, updating the LCD without flicker. Let's now look at the block diagram to understand how all these pieces come together. At the center is the 16F877A microcontroller, takes input from the keypad and controls all outputs: the LCD, fan, LEDs, and buzzer. This is a classic embedded system architecture, taking inputs, processing logic, and providing output responses. This learning phase laid the foundation for building the project, step by step from concept to code to simulation. The goal was to create a smart and realistic washing machine prototype using a microcontroller that can let users select wash modes, choose water levels, display status updates, run wash, rinse, and spin cycles, handle pauses and door open events, provide completion alerts. So basically, mimic a real world washing machine, but simulated using code and embedded components. For this, I used three important tools: MPLAB X Editor, This is where I wrote my code in embedded C, XC8 Compiler. It compiled the code and generated the hex files that runs on the virtual microcontroller. PICSimLab, a simulation environment where I could test this entire system virtually, including all inputs and outputs, without needing physical hardware. Essential peripherals for the prototype. LEDs. Each LED represented a specific stage of the watch cycle. Buzzer, used for audio alerts like end of cycle. Fan, simulated the motor. LCD, displayed real time status updates. Digital keypad was the main user interface. Now, the system required were defined as essential peripherals for the prototype. Our washing machine prototype integrates several key peripherals to provide a comprehensive and interactive user experience. Each component plays a vital role in simulating real world washing machine functionalities. LEDs. Each LED represented a specific stage of the wash cycle. Buzzer alerts, used for audio alerts like end of cycle. Cooling fan, simulated the motor. CLCD, displayed real time status updates. Digital keypad was the main user interface. Functional requirements for the smart washing machine. The washing machine prototype is designed to meet several key functional requirements, ensuring versatility and user control for an optimized washing experience. Multiple wash modes like daily, heavy, delicates. Water level settings auto, low, medium, high, max. Controls start, pause, stop, reset. Safety feature door open, detection, and response. Each of these features required careful programming, not only the logic but also the user experience. For example, long key press for selection, time delays to simulate real washing, status updates and alerts. All of this was designed and tested in simulation, and I ensured it worked like a real device. Now comes the most interesting part of the project demo. Now that we have covered the project overview, let's take a look at the actual implementation. This is the MPLAB where we have written and compiled the code for our washing machine project. We have several files in our project like header files, source files, washing machine function def.c. This file contains the main logic of our project. We also have digital keypad.h. This header file provides functions for interacting with the digital keypad. We also have timer.h file. This header file provides functions for timer-based operations. And we also have CLCD.h and CLCD.c. CLCD.h, this header file provides functions for interacting with the LCD display. Now, coming to MPLAB, MPLAB provides various features like code editing, compiling, and debugging. We can also use the built-in simulator to test our code before uploading it to the microcontroller. Now, let's see the project in action. I will demonstrate how the washing machine controller works using the digital keypad and LCD display. Now, let's build this main project, and when it is built successful, we'll get a hex file. This hex file we have to load in our PICSimLab to get the output. Now let's see the project in action. I'll demonstrate how the washing machine controller works using the digital keypad and LCD display. This is PICSimLab, a simulation environment where I could test the entire system virtually, including all inputs and outputs without needing physical hardware. So let's start. This is our CLCD display, and this is our cooling fan. This is our buzzer, and these are the pods LEDs, and these are the switches. Here we are using LCD 16 into 4. We have an option of loading a file and reloading and saving a file. And we have types of boards in which we are using PIC and we have many types of board. We are using PIC16F877A Microcontroller board. So let's start by loading hex file. This is our hex file which we have generated in MPLAB. After loading hex file, we begin by powering on the virtual washing machine using a digital switch, switch 5. Then CLCD displays washing programs. We can scroll and select these washing programs by pressing switch 4. Heavy, delicates, whites, stain wash, eco cottons, woolens, bedsheet, rinse plus dry, dry only, wash only, aqua, daily, then return to heavy. By long pressing the switch, we can select the washing program mode. Next, the machine prompts the user to choose a water level with choices like auto, low, medium, high, max. Once I'm selecting a level max by long pressing the switch. Once a level is selected, we can press the start button and the cycle begins. To start the operation, we need to press the switch 5. The system shows real-time status updates like washing. The fan starts spinning when the wash begins, simulating motor's operation. The CLCD shows countdown time. If the user wants to pause the operation, we need to press the switch 6. The fan stops and the timer halts. On resume, the cycle continues. To resume the operation, we need to press the switch 5. See, the fan starts rotating and the countdown begins. There is also a door open simulation. When a specific key is pressed, specific key RB0 is pressed, the system pauses and displays door open. If you long press it, it shows the message door is open. Please close the door. Once released, it resumes operation. At the end of the cycle, the buzzer sounds for 2 seconds and a message on the LCD says program completed. Now we'll check stop operation. We'll select any washing program by long pressing the switch. Then we'll select any water level mode to check the stop operation. We need to press switch 6 to stop the operation. Finally, pressing stop brings the system menu back to the main menu. This simulation gave me a clear understanding of how embedded system works in synchrony with real-time inputs and outputs. Let's discuss about project demonstration highlights and challenges and troubleshooting. We start our project highlights from fully simulated smart washing machine built using PIC16F877A Microcontroller in PICSimLab. User interaction via 4 into 3 matrix keypad to select wash modes, water levels, controls. Wash modes like daily heavy delicates, water levels like auto low, medium, high, max. Controls like start, pause, resume, stop, reset. Real-time status display using a 16 into 4 CLCD showing messages like washing, paused, door open, and program completed. Fan used to simulate the motor behavior during the wash and spin cycles. LED indicators used to represent various washing stages visually. Buzzer provides audible alerts at the end of the wash cycle. Pause resume functionality with state preservation. Door open detection and safety response like halts operation until the door is closed. All features were programmed in embedded C, compiled with XC8, and tested virtually using MPLAB editor and PICSimLab. Created a realistic industry style embedded system prototype without physical hardware. Now let's talk about challenges and troubleshootings. There were several challenges throughout this project, special, especially while simulating real world behavior using code. The first issue I encountered was with button debouncing. For instance, the start button sometimes triggered multiple operations. I resolved this by adding delay and state confirmation logic, which ensured that only a stable key press was accepted. Another challenge was with the keypad input. Detecting long key presses and distinguishing between short and long presses needed a fine balance of timer logic and flag handling. This was especially important for selection and confirmation steps. Controlling multiple peripherals like LCD, fan, buzzer, and LEDs in a synchronized way was also tricky. I had to manage timing and sequencing very carefully so that one event wouldn't interfere with another. This included handling LCD flicker, ensuring the fan started only during wash cycles, and activating the buzzer only once at the right moment. The simulation environment itself, PICSimLab, was a learning curve too. Mapping the keypad correctly and handling port configurations took a few iterations to get right. Sometimes an incorrect connection or mismatch in port assignments caused component not to respond, which required careful debugging. But with each challenge, I became more confident in identifying the problem, tracing it logically, and fixing it systematically. Internship project was a complete learning cycle in itself. I designed, coded, simulated, and tested a working prototype of a washing machine using embedded C and PIC16F877A. Here what I accomplished. Applied real-time programming using timers and delays. Managed multiple input-output devices like LCD, keypad, fan, buzzer, LEDs. Created a user-friendly interface for selection and operation. Simulated motor behavior and safety controls. Built confidence in debugging and problem solving. Most importantly, I learned how hardware and software integrate in embedded systems, something that will be essential in any future product development role. This project also taught me project discipline from requirement analysis, design, coding, testing to final documentation and presentation. I'm proud of this achievement and grateful for the support I received from the Emertxe. Thank you so much for watching my presentation. I hope it gave you valuable insights into how embedded systems can be applied to real world use cases. I look forward to continuing my journey in this field and applying these skills in upcoming industry challenges.